In experiment A, we have 25 degrees Celsius and it is without a catalyst, right? And then in experiment B, we have 25 degrees Celsius, but then now we have a catalyst. And the first question, 5.1, is saying in which experiment, A or B, is the reaction rate higher? Use the collision theory to explain the answer. So the only difference between experiment A and experiment B is the fact that we have a catalyst in experiment B, right? And then if we have a catalyst, the catalyst will lower the activation energy. So our answer here will be B. It will have a higher reaction rate. Why are we saying so? The first point is that the catalyst will provide an alternative route of lower activation energy. If that is the case, then more molecules will have kinetic energy, which is equals to or higher than the activation energy. And then lastly, more effective collisions per unit time. And then as a consequence, a higher reaction rate. So that is the answer to 5.1. Right, and now 5.2. Let's look at 5.2 and see what the question says. So 5.2, the Maxwell-Boltzmann distribution curves X and Y for the two above experiments are shown below. Identify the curve X or Y that represents experiment C. So let's go to experiment C and do some analysis. So experiment C is right here. The temperature is 35 degrees Celsius, right? And then in A and B, the temperature was 25 degrees Celsius. And then it is without a catalyst. So which curve, X or Y, is for experiment C? Curve Y is for experiment C, right? So the answer for 5.2 is Y. Why are we saying that? Now let me explain. Every time when there's an increase in temperature, right, average kinetic energy of the molecules is going to increase. And as a consequence, the Maxwell-Boltzmann distribution curve will shift to the right, and then the peak will get lower, right? As you can see here, Y is more to the right compared to X, and then it shifted a bit lower, right? That's what always happens when temperature is increased in an experiment. So that is 5.2. Now moving to 5.3. So 5.3, the volume of gas produced in experiment B during the first 3.6 seconds is collected in a syringe as shown below, right? And then 5.3.1, write down the volume of O2 collected in the syringe. So let's go ahead and do some analysis, right? So we can see that the O2 is filling this space. Now we just need to write down the volume, right? Let me show you something. From this point here to this point, it's 160, right? So obviously from this point here again to this point should be half of 160, which is 80, right? So we know that one marker is 80 centimeter cube. From 480 to this point we're interested in, it's just a matter of adding 80 centimeter cube, right? So we're gonna have 480 plus 80 being equals to 560 centimeter cube, and that is the volume of gas we have collected, right? And then 5.3.2, calculate the mass of water that was produced during the first 3.6 seconds. Take the molar gas volume to be 24,000 centimeter cube per mole at 25 degrees Celsius, right? So we have 2H2O2 giving us 2H2O plus O2. We have the volume of the oxygen, right? We want the mass of the water. So what we can do, we can convert this volume to number of moles, right? And then after finding the number of moles of O2, we're going to use those number of moles to find the number of moles of H2O. And from the number of moles of H2O, we're going to be able to find the mass, right? So let's go ahead and do that. For O2, we're gonna say that the number of moles is equals to the volume divided by the molar gas volume, right? We can only use this when we are dealing with gases. So this will be equals to, what is the volume? We say that it is 560 centimeter cube divided by our molar gas volume, which is 24,000 centimeter cube. Question now might be, why am I using centimeter cube and not decimeter cube? That is because all my units are in centimeter cube, right? So even if I divide the numerator and the denominator by 1,000, those thousands are gonna cancel out, so it doesn't really matter in this case. But anyway, stories. So we're gonna have 0.023 moles of O2, right? But let's not forget, we want to use the moles of O2 to find the number of moles of H2O. So we're going to say that the number of moles of O2 divided by the number of moles of H2O is equals to, what is the balancing coefficient of O2? Yeah, there is 1 here, right? So we just have 1, and the balancing coefficient of H2O, that is 2. So the number of moles of H2O is 2 times the number of moles of O2, right? So we're going to have 0.046 moles as the number of moles of H2O. So now let's go ahead and find the mass. We know that the number of moles is equal to the mass divided by the molar mass. So the mass will be equal to the number of moles divided by the molar mass. What is the number of moles again? 0.046. The molar mass of H is 1, right? But then we have 2 hydrogens, so we multiply that by 2. Plus the molar mass of oxygen, which is 16, right? So if you put that in your calculator, you should get 0.83 grams. So that is the mass of H2O, which is produced during the first 3.6 seconds. Right, let's do 5.4.1. So we have a graph which is not drawn to scale. It is obtained for the mass of oxygen gas produced over a period of time in experiment A. And then the first question is saying write down the rate of production of oxygen gas for the interval 30 seconds to 36 seconds. So let's go to our graph. We have 30 seconds right here, right? And then this is the mass of oxygen, and then 6 seconds later we have 36 seconds here, and the mass of oxygen has remained the same, right? So the change in the number of moles is 0, right? So that will tell us that our rate of production is 0 grams per second, right? There's no oxygen being produced anymore, right? Our reaction has been completed. And now 5.4.2, will the rate of the reaction in the interval 3 to 9 seconds be greater than, smaller than, or equal to the rate of reaction in the interval 9 to 20 seconds? In the interval 3 to 9 seconds, it's going to be greater than. It's going to be greater than, right? The question might be, why are we saying it's going to be greater than? Let's not forget that at the start, we have a lot of concentration, right? We have a lot of number of moles. But then as the reaction goes on, then we have less number of moles. And let's not forget what the collision theory says about the concentration. The higher the concentration, the higher the rate of the reaction. So as we lose number of moles, then the reaction rate sort of goes down. And then 5.4.3, the average rate of decomposition of hydrogen peroxide is 2.1 times 10 to the minus 3 moles per second. Let's calculate the value of time t on the graph. So we're looking for this time here. This is where our reaction ends, right? So let's jot down the information we have and see which technique we can use here, so to say. So we have the rate of reaction of hydrogen peroxide, which is 2.1 times 10 to the minus 3 moles per second, right? And then what else do we have? Let me see. We can say that the rate of reaction is equal to the change in the number of moles divided by the time, right? So if we use this equation, we would be able to find the time, which is what we are looking for. The rate of reaction, we have it, so we just need to find the number of moles, the change in the number of moles of hydrogen peroxide, right? If we do that, we have the change in time, we have the value of t, right? But then how can we possibly do that? We have the mass of O2 which is produced, right? We can convert this mass to number of moles, and then after converting that mass to number of moles, we're going to use it to find the number of moles of hydrogen peroxide, right? And then substitute in this formula, and we are done. Again, grade 12 chemistry, the first half is organic chemistry, and the second half, you're just trying to find the number of moles. So let's go ahead and do that. So for O2, right, we have a mass which is 0.9 grams, right, at time t. Yeah, it's easy to see them. And then the number of moles will be equals to 0.9 divided by O2. So O2, that would be 16 multiplied by 2, right? So we have 32, and then if you put that in your calculator, you should get 0.028 moles. So we have the number of moles of O2. Now let's use the number of moles of O2 to find the number of moles of hydrogen peroxide. So we're going to say the number of moles of O2 divided by the number of moles of H2O2 is equals to the balancing coefficient. The balancing coefficient of O2 is 1. That of hydrogen peroxide is 2. So the number of moles of hydrogen peroxide is 0.028 multiplied by 2, which is 0.056 moles. So yay, we have the change in the number of moles of the hydrogen peroxide, right? So now we can substitute it back here into our formula, right? So let me do that. The rate of reaction is 2.1 times 10 to the minus 3. The number of moles is 0.056. Let me make sure. Yeah, 0.056. And then we have delta T here, right? You know, you just apply a bit of math and you get delta T being equals to 0.056 divided by 2.1 times 10 to the minus 3. 26.67 seconds, right?